Okay, so now we're going to pursue our endeavor of computing an equilibrium, a general equilibrium, in a Markov setting with one period arrow securities being traded, complete markets in arrow securities. And one way we're motivating this is we're going to create a theory of Q, which is our n by n pricing kernel, arrow securities prices. So to review our setup, and this is very much a version of what's in chapter 9 of RMT5 with Lundquist. We're going to have a Markov chain. We're going to have n states. We're going to have a Markov chain P. We're going to have some exogenous endowments. We're going to name the people K equals 1 through K. Those are the names of our people. Person number K has this endowment vector across states. So the endowment depends on the state of the kth person. If we add up all the endowments across people, we get this aggregate endowment. So it's that aggregate endowment that the economic arrangement is going to allocate in every Markov state. And we're going to have a collection of consumptions to person K in state S. So K goes from 1 to K, and S belongs to this set 1 through N, those Markov states. We have a definition of feasibility. An allocation has to respect the feasibility restriction that there has to be enough goods for the allocation to people. And this has to be true for every S, for all S. So that has to be true. And we're assuming that there's no association in utility. So this feasibility constraint is going to be satisfied at equality. So a common preference specification is this one, which we're going to use. We've been using it throughout. It's discounted expected utility of consumption over time. So we're going to have this utility function and this discount factor. Okay. We'll make some more assumptions about this. So these are going to be the inputs to our analysis. We can think of what are the outputs. Well, one output is going to be this pricing kernel. We're going to have an allocation. We're going to have a distribution of wealth, and it's going to be a vector alpha. So what it's going to be the fraction of wealth. Alpha sub K is the fraction of wealth that is owned by person K. And those fractions are going to add up to 1. And one of the things that we want to determine, this is an equilibrium object. Okay. And then we're going to have a collection of consumption. We're going to have a consumption allocation. So this is an allocation. Okay, we're going to assume, and there's content in this, that the one period utility function is this CRRA form. And that's going to have the implication that the marginal utility of consumption is given by this power function. Okay. So now we're just going to be in the business of assembling equilibrium conditions that we've already derived earlier. So one thing that we derived was the first order conditions for a household trading euro securities are going to be of this form. You know, what the household does is he takes Qij as given, and adjusts his choices of consumption in state J and in state I to satisfy this relationship. These PIJs are, he knows those. Beta is a characteristic of this. So beta and gamma are preference parameters. Decision theorists would say PIJs are also preference parameters. They tell something about how the person, look at this, how the person feels about trading off consumption at different states. Okay, so from the point of view of the individual jiggles the consumption to satisfy this relationship, taking these prices as given. But you know, we're the analysts. We want to compute the prices. Okay, so a key thing is, so with general preferences, we would have to compute the Q's and the allocation. We would have to compute these simultaneously, and the distribution of wealth. We would have to compute all of these things simultaneously, that would involve solving a system of simultaneous equations, and it would be convenient if we didn't have to solve them simultaneously, if we could solve them recursively. So this is kind of a seek and ye shall find. So there's a set of restrictions on preferences that we have made so that we don't have to solve them simultaneously. We can solve them recursively. And the key thing is, with CRA preferences, individual consumptions are going to vary proportionately with aggregate consumption. And therefore, in an exchange economy, with the aggregate endowment. So this is a key thing. And this is going to allow us to simplify things immensely. So it's going to turn out that, so let's see how this puts together. It's going to turn out that with CRA preferences, what are known as angle curves are going to be affine in wealth. All that means is they're going to look like they're going to be affine in wealth, and as a consequence of that, I should say this is a consequence. As a consequence of there being affine in wealth, what's going to happen is consumption of a person K is just going to be, it's going to satisfy this equation. It's going to be in state S is just going to be a constant alpha K that's not going to depend on the state times the aggregate state times the aggregate amount of endowment. So this is going to be true for person K. There's going to be one such for person K. And if I take this thing and I substitute back in here If I substitute that back in here, that's the way this is going to fit together. This equation is just going to become like this. Qij is equal to beta. And then this is just going to be y aggregate in state j divided by y aggregate in state I raised to the minus gamma times Pij. And this is going to be my formula for the equilibrium asset pricing kernel. And what's happened there is the alphas canceled out because they're both the numerator and the denominator. And all that mattered was the aggregate amount of income. So this equation is going to be true for all k, but we're going to use it just on the basis of the aggregate. So this Gorman aggregation is it's as if there's a representative consumer to whom we impute the same preferences that we give our individual persons with these power utility functions. If there's a representative consumer who consumes the entire endowment, and we don't worry about the alpha k's, the key thing is the alpha k's dropped out here. They divided out. So we could, when we compute the Arrow-Debreu pricing kernel, we just, the way we've rigged it is we can just forget about distribution. We have to worry about it later. Okay. So to proceed, here's our formula. That's what we're going to do. Okay, so now that we have this, so look what we've done. We have endogenized Q. That's what we were after. And this is used over and over again. This is, this is a version of the famous Lucas asset pricing formula. Hansen and Singleton have used it over and over again in a really important work. So we've derived it in our particular setting. Okay. So now what we want to do is we want to compute values. Okay, so what I want to do is I'm going to let I'm going to need some values, and I'm going to kind of use asset values. I'm going to do some asset pricing. So I have this formula that I'm going to apply that I got from asset pricing. So I'm going to let I'm going to view the individual as an asset, and I'm going to get a vector of state-dependent values of individuals' endowments. So I'm going to treat the agent like a cum dividend stock. I'm just going to value his or her endowment. So I'll define those. This just looks like our price vector before. And what this is it's the value of individual consumers' endowment stream. Okay, so where I've just stacked up their endowment across states into a vector like this. So now this is going to be, why am I doing this? It's because Arrow told me I had to do it. Arrow told me I had to do that. Okay, because these things, what are these things? These are the natural debt limits. This formula is our formula for the natural debt limits. It's the value of the person's endowment. It's the most he or she could ever repay in terms of a debt, on the assumption that he or she consumes zero from then on. Could never get more from this person. So that's the so-called natural debt limit. it's the weakest debt limit that it's even physically feasible to impose. So we've computed the natural debt limits, and remember we had to do that before to get going with our trading of euro securities. Then another thing, now let's go into the next thing is going to be continuation wealth. That was a key thing we wanted to compute. Well, that's going to be just as easy to compute using our insights from asset pricing theory. I'll call those continuation wealth. It's going to be a well, we could think of it as it's going to be a set of vectors that look like this. This is a vector of continuation wealths in state S. And there's going to be one of these. So the way to think of this is going to be a K by N matrix that I'm going to form. Those are my continuation wealths for person K in state S. That's the way I'm going to read that. And each individual has one. That's what I've read. So, so continuation wealth of person of this person is going to be we can compute it just from this formula, and this is the so what this is going to be. This is the person's consumption. It's a vector of consumptions, state by state. So what does the person consume? Consumes alpha k y in state S. And that's what it consumes. That's what the person, that's an endowment. That's the person K's endowment in state S. This is a vector. I just so if I want to know what's the continuation value of the person, it's got to be this. And I'm just translating, applying our formulas to what we did when we went through and constructed an equilibrium with a competitive equilibrium with trading of euro securities. But I needed those continuation wealths. And okay, those look like that. So, and we're going to require, actually, if you check this out, this implies that, this implies this inequality, that continuation wealths sum, if we have a feasible allocation, continuation wealths sum to zero. They sum to zero. So what do we know about continuation wealth? They sum to zero, and at the initial state, S0, the continuation wealth is zero for every person. Because what does that mean? We're beginning this economy with everybody being debt-free and asset-free at state zero. So there's a particular state, the initial state, where everybody starts with zero wealth. But then as trading proceeds, continuation wealth change. There's borrowing and lending, state contingent. So my continuation wealth may go down and yours goes up because we've traded one period euro securities. Okay? So now, what are optimal portfolios? Well, we've already computed them. Optimal portfolios, we saw this when we studied euro securities. We're just going through and computing, when a Markov setup, the objects that comprise competitive equilibrium with trading of euro securities. So the asset portfolio that the person chooses in next period in state S is just equal to the continuation wealth. So the portfolio choice equals continuation wealth. Now, see what we're using a tricky kind of back solving technique. Um, we're using lots of insights that we got already from chapter 9. So where am I using them? Well, so what to get this, I'm using them. I already know that the equilibrium allocation equals the solution of the planning problem. It equals the planning allocation. And what the planner did is he or she just took these the aggregate endowment and he assigned everybody shares, constant shares of the aggregate endowment, constant across states, constant across time. So these are these alpha k's. So we know there exists there's some constant alpha k's. We don't know what they are yet. We'll have to figure out what they are. But if we knew what they were, so we need the alpha k's to compute continuation wealth. We need the alpha k's to compute the therefore to compute the portfolios, and we don't have them yet. Um, um, but we're going to get them soon. Okay, so uh, that's what we're going to get now. So here's the key thing. At state 0, we have to have everybody's equilibrium wealth. Everybody's continuation wealth at state 0 has to equal 0. And this has to be true for all k, not just for the sum. And, this is, I hesitate to say this kind of matches up with imposing, there's a sense in which this is the equivalent with imposing the times 0 budget constraint that we impose in the Arrow-Debreu times 0 trading setting for everybody. That's the counterpart of it. So if you take this, I apologize, I've been kind of ambivalent about subscripts or superscripts. If the alpha k assigned to one person, the alpha k is going to be equal to, I'm going to do it this way. It's the, let's stare at this. Okay, there's going to be some notation. What we're going to do, so we're in state 0, and it matters that we're in state 0. So now we're kind of adopting the attitude of which I like, Bob Lucas said we should like it, attitude of a computer programmer. His statement was, if you really had a model that was worth its salt and you really understood it, you could write a Fortran program to program it up and simulate it. Well, nowadays we'd say we could write a Python or Julia program to program it. So that's what we're doing. Okay, so what we're going to do is we're going to take this is going to be the row of, this is going to be the row of I minus Q inverse. Now that's this thing is how we price this operator, I minus Q inverse. That's how we price an infinite stream, which is great. So we're going to take that row. If you take that row that corresponds to the initial state and you apply it to my endowment, that's my equilibrium wealth. And in the denominator, that's the equilibrium wealth of the whole economy. So this alpha K is my share of the wealth relative to the whole economy. That's what this formula is doing, saying that. That's my share of wealth relative to the whole economy. So, do I have everything I need to compute this? Well, the answer is yes, because what do I need? YK Yes, that's exogenous. The denominator is just the sum of the YKs, state by state. That's exogenous. What's not exogenous is this V, but what that V is that's the row of I minus Q inverse that corresponds to the initial state I started. So notice the state I start in this Markov setup is going to affect equilibrium wealth, the equilibrium distribution of wealth. So now that I've computed, notice this, the logical flow is, now that I've computed this, I can go back and compute, I have to compute a bunch of stuff simultaneously. In some sense, I can now know, what do I know? I know the borrowing limits, I know the natural debt limits, and I know continuation wealth. So now with everything that I've computed, I can put it together and I can verify that I have constructed a competitive equilibrium with sequential trading of one period arrow securities. That's the way how all this stuff fits together. Okay. So that's what we did. So let's see if we can live up to what Lucas said. He said if you can, in a real life applied model, you should be able to write a Fortran program. Well, here's Python program. We've written a Python program, and there's going to be no required Python programming in this class. But here's Python looks a lot just like writing down the math after you do some bookkeeping. So we're going to compute a we're going to compute a pricing kernel, which is just it's going to be what this code just is. It's going to tell me beta Qij times U prime of Yj over U prime Yi. That's what that code does, and so on. So we've written this, and what we're going to do next is we're going to construct some examples of economies, and the way we can read this example is I'm going to just begin with there's going to be two people, there's going to be two states. The transition matrix is going to be really boring. It's going to be essentially IID. And then I'm going to have a default value of beta. And then I'm going to make up the, look what I'm going to do here. I'm going to have person number 0. The values, the endowment takes on values 0 and 1. So person 0 gets the endowment 1 minus S. The other person gets the endowment S. They add up to 1. There's no aggregate risk, but there's a lot of risk at the individual level. So, and then just by changing new matrices, putting on new matrices, we'll be able to study some other examples. So we're going to do that the next time that we meet.